Okay, so for this second week, we're going to be talking about probability. And this is going to build on what we learned last week with counting different possible outcomes. But we're going to start using that idea to be able to calculate the probability of simple events happening. So we're going to start with just kind of the basic idea of what probability is. And then once we run into some problems with thinking of probability that way, we'll get into some other ways of thinking about things. Today, we're going to be specifically talking about what happens when we have multiple independent events happening. And then later on, I think we'll do this next week, is what happens when those events are dependent on each other. That gets more complicated, and we'll save that for next week. So the vocabulary you're going to see today, experiment just refers to something happening, things like flipping a coin or rolling a dice. Sample space, we'll talk about event, probability, independent, and dependent. And our goal for today is to cover these first two this week. And then next week, we'll talk about that one. So our first thing, an experiment, just a process that has a definite set of results. So like I said earlier, tossing a coin, rolling a die, drawing a card, something that you can list out all the possibilities of. And then that leads into this idea of a sample space. So a sample space is just that listing of all the possible options or all the possible what we call outcomes of an experiment. So for something simple like tossing a coin, we've only got two different outcomes, presuming that we're tossing just a normal coin. And so for us, that's just that we could either get a heads, we could get a heads, or we could get a tails. Those are the only two options. And we just put those two different options into these curly brackets. I can't really draw those very well, but that represents our sample space. It's just the only two possible outcomes that we have. Once we get bigger things, something like tossing a coin 2 times, we've got a little bit more complicated things to think about. So if I were to toss a coin twice, one of the possibilities was that I could get heads both times. I could also get something like heads the first time and then tails. Or I could get tails the first time and then heads. Or I could get tails the first time and tails the second time. And so this represents the 4 different things that could happen when you toss a coin twice. Each of these elements of our sample space consists of 2 separate things, but there's 4 items here, 4 different possibilities for that flipping a coin twice. Okay, how about something like rolling a die? If we just have our normal standard die, when I say that, unless I say something else, it's going to be a 6-sided die. Our chances are just 1, 2, 3, 4, 5, and 6. Or something like drawing a card, this gets more complicated, or not really more complicated, but a lot longer, obviously. There's 52 different cards. And so I could have something like the ace of hearts, or the ace of, can I draw a spade? No, I cannot draw a spade. But each of those 4 suits has, all of the cards. And so we'd have to list those all out separately. Ace of hearts, ace of spades, ace of clubs, ace of diamonds, 2 of clubs, 2 of spades, 2 of hearts, 2 of diamonds. There'd be 52 possible answers there. Now, before we move on, just one quick note here. All of the things that we're going to be looking at are going to be events that are equally likely. So all that means is that we're talking about basically fair dice, where when we roll a dice, we're equally as likely to get a 1 as we are to get a 6. Later on, we will talk about events where one outcome is more likely than the other, and that gets a little bit more complicated again. So for today, you're going to look at everything in being equally likely. That doesn't mean you're going to get that. If you flip a coin 10 times, it doesn't mean you're going to get 5 heads and 5 tails, just that you're equally likely to get a heads and a tail each time. Okay, so our first definition here, our first thing we're going to talk about, simple probability. The simplest way to think of probability is that we take the number of ways that what we want to happen can happen and divide it by the total number of things that could possibly happen. And so a way to put that is the number of desired outcomes over the total number of outcomes. If we're looking at things like, flipping one coin and getting heads, in that case, the number of desired outcomes would be the number of ways we get heads, which is just 1. There's only one way to get a head when you flip a coin, over the total number of possible outcomes, and there are 2 possible outcomes, so we have 1 out of 2 or 0.5 for our probability. And that'd be the probability of getting a heads. Now, obviously, they're not going to stay that simple. So let's take a look at some examples here. How about something like this? The probability of drawing a queen from a deck of cards. So think about the things that we need to know from that. And then I want you to think about what the probability would be. Okay, so in order to calculate this, we need to know two things. We need to know how many ways can we draw a queen. In other words, how many queens are in that deck. And there are 4 queens in a standard deck. And we also need to know how many total cards there are. There are 52 total cards. And we obviously want to not leave it that way. We don't want to leave it as a 4 out of 52 or an unsimplified fraction. So that would be 1 out of 13. Or if I want to put that as a decimal, which I guess I will, 1 out of 13 is about 0.06 or 077 if we wanted to put that as a decimal. You'll notice here that probabilities are always usually going to be listed as decimals. You might have seen something like this being written as 7.7%, but we don't typically do that in math. A probability will always be a number less than 1. Okay, let's take a look at this. The probability of getting 2 heads when you toss a coin 3 times. So this one's going to be a little bit more tricky. It's a little harder to count these all out. The first thing you want to be thinking about here is how many different options are there when you toss a coin 3 times. And if we go back here, when we tossed our coin once, we had 2 options. When we tossed our coin twice, we had 4 options. If you can kind of follow along on that pattern, this is 2 to the first, 2 squared. The next one's going to be 2 to the third. There's going to be 8 possibilities total. And this is a case where listing them out, even though it kind of seems annoying, can be really helpful. So our possibilities could be something like all heads. We could have heads, heads, tails. Then we could go heads, tails, heads. Then we could go heads, tails, tails. Then we've got heads. Then we want to do tails. Heads, heads, tails, heads, tails, and then finally tails, tails, heads, and tails, tails, tails. So those are our 8 possibilities. So our total for the bottom of our fraction here has got to be 8. And if you look through, how many of those are 2 heads? Well, that's 3 heads, so that doesn't count. There's 2 heads. There's 2 heads. That doesn't count. There's 2 heads. Not that, not that, not that. So we've got a total of 3 out of 8 ways of getting 2 heads when we flip our coin 3 times. And just to get a decimal there, 3 out of 8 is 0.375. And so that would be our probability of getting 2 heads with a tossing a coin 3 times. Now, this is something that you realize would get a lot harder very, very quickly. If I wanted to know what's the probability of getting 4 heads when I toss a coin 5 times, suddenly I'm looking at 32 different options that I'd have to sort through. So it'd get a little trickier. Okay. So let's just do a couple more that are a little bit more tricky, and then we'll find some better ways to handle these. So first things up, find the probability that a 5-card poker hand is all spades. Now, there's a lot of possible poker hands. There's no way we could possibly list all these out. But if we go back and think about something that we learned last week, we can work on this. So this probability is going to be the number of all spade hands over the total number of hands. And those two things separately we can work out because we learned how to do that last week. So for this top, we have to decide how many spades are there total, and then how many ways are there to pick 5 of those. And then we also have to think about, does order matter? And in this case, in a poker hand, the order you're dealt the cards doesn't matter. So we're using a combination. So we've got 13 spades. We're going to choose 5 of them. That right there represents this number of all spade hands, the number of ways we can get 5 spades out of this deck. Then for the total number of hands, again, order doesn't matter here. So we're going to do 52. All 52 cards, choose 5. This number on the bottom represents the total number of poker hands that are possible. And so when we calculate that, we'd have to definitely use a calculator here. We're going to do 13, choose 5, which again is just saying there's 13 total spades divided by the 5 cards we want. And then divided by the 52, choose 5, which is saying that there are 52 cards, and we're picking 5 for our hand. And so we've got this in scientific notation here, 4.9 times 10 to the negative 4, which means we're moving our decimal place 4 spaces over. So we'd have 0.00004, what was it, 0.0495. So a very, very low probability that we'd have all spades, also known as a flush. Now we could also have all hearts, all diamonds, all clubs too. So if you were to look up what's the probability of getting a flush in poker, it'd actually be 4 times that size. Okay, so take a look at this one and see if you can try to figure that one out for me. Irene has 4 blocks, an A, an M, an H, and a T. What is the probability that she spells math? Keep in mind she is 1. She doesn't know how to spell yet. Okay, so when we calculate this probability, again, we need to think about what are the number of possible desired outcomes over the total number of possible outcomes. Now here we only have one desired outcome, that it goes M-A-T-H, so only one at the top. Now on the bottom, we got to figure out how many ways can she possibly arrange those 4 letters. And again, going back to our counting principles, we've got to think about that. There's a couple ways we could do this. We could use this as a permutation to basically say we're going to take our 4 letters and we're going to pick 4 and order matters. Alternately, we could think about that with our spaces. We've got 4 spaces to fill in, 4 possibilities for the first one, 3 for the second, 2 for the third, and 1 for the fourth. Those 2 expressions are equal to each other. And so again, we could go to our calculator. 1 divided by 4, pick 4. And we've got 0.0416 as our probability there. Now, those are obviously getting pretty tricky. So let's think about this a different way now. This is where we're going to get into independent events. Now, it's important that we call these events are actually independent of each other, which means that the first event isn't going to be affecting the probability of the next event, or at the very least that we can adjust for that in some way. So the probability of 2 events happening, probability of A and B happening, is just the probabilities multiplied together. We hear this called the multiplication rule for probability. So if we want the probability that you roll 2 dice and get 2 6s, we can look at those dice separately. The probability that we get a 6 on the first dice is 1 out of 6. The probability that we get a 6 on the second dice is 1 out of 6. And the multiplication rule says multiply them. So we've got a 1 out of 36 chance of getting 2 6s when we roll 2 dice. Those 2 dice are completely independent of each other, and that's what lets us do that. Now, when we look at this next example, the poker hand again, you're going to argue with me that this isn't independent. When I pick the first card, the chance of getting a spade again on the second card is going to be different. But what we can do here is we're going to make it so that we've accounted for that missing spade for the rest of these hands. So in our first card, what's the probability that we draw a spade the very first time? Okay, so if you're thinking about this, we've got 13 spades and there are 52 total cards. So we have a probability of 13 out of 52. Now for our second card, the difference here is we have to assume that we've already got that spade. And so there's not 13 spades left, there's actually only 12 left. And the same thing in the bottom. There's no longer 52 cards, we've drawn one of them out right here. There's only 51 left. And we keep going with the same kind of idea. Next one we'll have is 11 out of 50. Then we'll have 10 out of 49. And finally, the last one is going to be a chance of 9 out of 48. And so if I go to Desmos and go ahead and calculate that out, 13 out of 52 times 12 out of 51 times 11 out of 50 times 10 out of 49 times 9 out of 48, you're going to see something here. You have the exact same probability as the one we calculated up above. We have that 0.000495. So everything stays the same. No matter how you choose to calculate this, you're going to get the same answer. That's obviously got to be the case, or it wouldn't be correct. But two different options here. Thinking of these as separate independent events, 5 separate cards, is a lot easier than trying to count the number of ways to get all spades. And so this is a nice trick, as long as you can adjust for the first card being taken out and then the second card being taken out, and so on. Okay, so obviously you already have the answer for this, so I'm not going to have you do that one. But if we wanted to think about this one the same exact way, we can. So we'd want to think about this as 4 separate independent events, and basically the idea of placing each letter correctly. So what's the probability that she places the M correctly the first time? Well, she's got 1 correct place to put it out of 4 possible choices. Now, once she's placed that M, she's got 3 letters left. So there's 1 correct out of 3 possible letters. The next one, she's still got 1 correct, the T, out of 2 possible letters. And then the fourth one, as long as she's got the first 3 right, there's only 1 option left. So she can't get that last one wrong at this point. And again, if you look at this and think about what that fraction would be, I'm going to go ahead and put it back here. You'll notice that looks exactly the same. 1 over 4, 1 over 3, 1 over 2, 1 over 1. And so that's going to be exactly the same there. Just a different way of thinking about it. Okay, so we got one last thing to talk about here, which is mutually exclusive events, or the probability that one thing happens or another thing happens. The key here is this idea of mutually exclusive. It has to be written so far so that not both can happen at the same time. That it's not possible that they're both true. So after we do this first one, we'll talk about an example that wouldn't work here. So our first example here is, what is the probability of drawing a 5 or being your key word here, a face card? When you see that word or, you're going to be doing some adding. So the probability of drawing a 5, how many 5s in your deck of cards? Well, there's 4 of them. So I'm going to do 4 out of 52 for the 5s. Or a face card. How many face cards are there? Well, there's all the jacks, all the queens, all the kings. So there's a total of 12 of those. And again, there's 52 of them. And so when I add those together, I get the total of 16 out of 52. And that is obviously going to simplify. If I want it as a fraction, I can do that, 4 out of 13, or about 30%. About 0.3. Now, the reason this works is because there's absolutely no way you could draw a number that is a 5 and a face card. There's no such thing. Now, let's do an example here of one that wouldn't be that way. If I asked you a question like this, what is the probability of drawing a 5 or a club? There's a problem with that because there is a 5 of clubs. If we did it the way we did it up here, with the probability of drawing a 5 as 4 out of 52, and the probability of drawing a club as of 13 out of 52, we'd be counting the 5 of clubs twice. And so we'll talk about that next week, how we deal with that. If we wanted to calculate something like this, the probability of drawing a 5 or a club. I should say or. So at this point, I think you're going to have some homework questions Remember, there's going to be office hours to Tuesday, which if you're looking at these right away is today. Those are from 9 to 10. And then on Thursday from 1 to 2. You can always email me if you have any other questions, although just keep in mind it is a whole lot easier to answer these sometimes one-on-one or face-to-face rather than over email. Also, keep in mind that if you turned in your homework, hopefully before the absolute deadline here, I should have it back. Take a look at those scores on Canvas, and you can certainly redo any questions that you want to improve that grade. Other than that, hopefully I see some of you during office hours, and have a great week.